Back. So the second speaker today, and also the last speaker, is Cong, also from Jussieu, and she will speak about the cohomology of spaces of shtukas. So, go.
Thank you very much for the invitation. So today I will talk about shtukas with many poles, working on some curves. So I show in the picture. So there are some geometric objects which relate the two sides of the Lagrange correspondence. And those geometric objects for number field, they are the Shmurda varieties. And for function field, they are the stack of shtukas. In my talk today, we will stay always on the function field, and we will talk about the stack of global shtukas and their cohomology. So that's where we are today. And so here are the settings. Let X be a smooth, projective, geometrically connected curve over a finite field. We note F is function field. And let J be a connected reductive group over the function field. And to simplify, we will suppose that the group is split and semi-simple. For example, ICLN. So here we have the space of automorphic forms. So let this A be the ring of Adele of the function field, and O the ring of integral Adeles. We have the vector space of automorphic forms for the function field F. So it's a space of continuous functions with compact support on this set. The J of A quotient by JF in one side and quotient by JO on the other side, with coefficient in QL. I didn't say L is not equal to P, L is another prime. So this is a space of automorphic form. And for function field, we have some special things. That is the boundary. So this is a very classical boundary, it has nothing to do with the boundary in Laurent's talk. It's a classical one, which is a classified stack of G bundles over X. X is our curve. So it's for any affine scheme S over the finite field, its S point is G bundles over X times S. What we have here is that the FQ point of boundary, which means the G bundles over X, this set is isomorphic to this set of double quotient. In the following, when we talk about space of automorphic forms for the function field, we will use this space, the continuous function with compact support over the FQ point of boundary. And the stack of shtuka are some kind of generalization of FQ point of boundary. So here they are. To define the stack of shtuka, we will need the Lagrange dual group of G. So we denote G height, the Lagrange dual group of G over QL. To each finite set and each finite dimensional QL linear representation W of I copy of G height. So G height I means I copy of G height. To each I and W, we associate a classified stack of shtukas. The definition is the following. For an infinite set of affine scheme S over FQ, the S point of shtuka is the following groupoid. The data there you have the I point of the S point of the curve X1, Xk, and you have a chain of G bundles. So G0, G1, until Gk minus 1, they are G bundles over X times X. And you have a chain of modification such that the last one, the tau G, this is the inverse image of Frobenius of the first one. So this means the inverse image of Frobenius on X, the total Frobenius on the scheme X. Between these G bundles, you have some modification, which I mean that it is an isomorphism everywhere and except on the poles. So phi1 is the isomorphism outside X1, and you have some modification on X1, which is bounded by W. And I didn't write down the precise definition here. So the modification is only at the infinitesimal neighborhood around X1, and the modification is bounded by W. For phi2, the modification is only around the infinitesimal neighborhood of X2 and also bounded by W. So you have so between G0 and tau G, you have isomorphism outside all the poles, and around poles you have some modifications. Why it's a generalization of FQ point of function? Because when your set is empty, which means you only have G0 and tau G0, you don't have modifications. So you have G0 G bundle over X times X, which is isomorphic to its inverse image of Frobenius. In that case, your G tensor G0 in fact comes from X. It is a G tensor on X. So it is exactly the FQ point of boundary. So when there is no pole, your stack of shtukas is FQ point of boundary. And when there are poles, it's something more general. So you always have a morphism from shtuka to I copy of the curves. With you send a shtuka this data to only to this pulse. As an analog, so for number field Q, for example, you have the curve spike Z, and you have Shimura varieties over spike Z. You can view it as some kind of shtuka with one leg. And for function field, so analog of Q is F, and analog of spike Z is X. But here you have something different, is that you can take X times X. So you have stack of shtukas, you can over any arbitrary copy of the power copy of X. So you can have many different powers. And more generally, you can have a stack of shtukan with level structure as a Shimura variety with level structure. And so you take N a closed subscheme of the curve. We can define stack of shtukan with level structure on N. So they are over the copy of curves outside the level structure. You always have the morphism of poles. The stack of shtuka, they are always the linear Mumford algebraic stack. But in general, they are not smooth and they are not proper neither. We will consider the relative cohomology of some sheaf on shtuka push forward to the I copy of the curves. So what sheaf we consider on the stack of shtuka? So the stack of shtuka has a local model, which is Benson Drinfeld Afan Grassmannian associated to I and W. So on Benningsen Drinfeld Afan-Grassmannian, we have the canonical zeta k sheaf comes from geometric zeta k equivalence of Minkowitz and Villolin. And we can pull back these zeta k sheaves to shtukas. Thus, we get some zeta k sheaf on stack of shtukas. We note the F and with the same indices. In the cohomology, we consider what we call cohomology is the push forward of this canonical sheaf to the curve. So the push forward of this sheaf on the curve. So it's you can consider a degree J sheaf for any degree. It's a degree J of direct image of your canonical sheaf. So this is a QL sheaf or a copy of X minus N. So this is a morphism that we use. It is an inductive limit of contractible sheaves. So in fact, the stack of shtukas, they are forming locally of finite type, but they may not be of finite type. Here we use the Hadana-Hashman stratification on stack of shtukas. We write it as union of open substack bounded by the Hadana-Hashman stratification, and each open substack are of finite type. And for the cohomology, we take inductive limit of the direct image on each open substack. Like this, we obtain an inductive limit of contractible QL sheaves. The cohomology is a kind of generalization of space of automorphic forms. We have already said that when I is the empty set and W is the trivial representation, so the I copy of the curve is just a point, and the stack of shtukas with no legs is just FQ point of boundary when they can all have the level structure. And the cohomology in this case is just the function with compact support on the FQ point of boundary. So we refine our space of automorphic form. And here is the result I want to talk in this talk. So the theorem says that the relative cohomology sheaf over I copy of X minus N, it is unsmooth. The definition of unsmooth is that it can be written as an inductive limit of smooth QL sheaves. So there are some remark of the theorem. So here I write down the QL coefficient, but we have the same result for the cohomology with coefficient in ZL. And there is an application of the theorem is that so in the recent work of all these authors, they have a conjecture of the geometric Lagrange for the function field with an analytic coefficient. So their conjecture is a categorical conjecture. When one side you have the sheaves category of sheaves on log 6 for G height, and on the other side you have the category of sheaves on boundary. So all the category are derived category, and all the stacks are derived stacks. And to to have a connection with this categorical conjecture with the classical Lagrange conjecture for function field. They have this result is that when you apply a trace of Frobenius on their categorical conjecture, you get the classical conjecture for automorphic forms. So one step is that for the set of boundary, when you apply trace of Frobenius on the category of shifts on boundary, so the trace of Frobenius on a category is a vector space, and they prove that this vector space is exactly the space of automorphic forms for the function field. And in the proof of this, they use they need to know that this relative cohomology is unsmooth over the I copy of the curve. And slightly more general version of this is that when you apply the Frobenius on the Frobenius composed with the Haeckel operator on the category of shifts on boundary, you find the cohomology group of stack of shtukas. So when you consider Haeckel, you find the cohomology of stack of shtukas, the cohomology group. So that's about the theorem. And now I want to talk about conjecture. So let's begin by example with the one pole. So let I be a singleton. In this case, we have a shtuka is just over one copy of the curve. And we have the shtuka with the level n. This one is defined only over x minus n, defined only outside the level. You have a map from shtuka with level to the restriction of shtuka without level on the level. So you have a Galois cover of this. We have said that we saw that we have a canonical Sadake shift, the F and IW, on the stack of shtuka with level structure. We can take the direct image of the shift on shtuka without level structure. So this one, so this one, we have the direct image of this shift on shtuka without level structure. And the theorem in last page says that the direct image of this shift is unsmooth outside the level. Now we are interested in what happens on the level. So now we go further. Let eta be the generic point of x, and we take eta bar a geometric point over the generic point. For any geometric point v bar on the level, so v is a closed point in the level and v bar a geometric point. And for any specialization map, we have a canonical morphism from the cohomology with compact support of the special fiber of shtuka with coefficient in the nearby cycle. So our shift is pi exclamation en bar f is over this one. We have nearby cycle on this one. We have canonical morphism from cohomology of special fiber with the value in nearby cycle to cohomology with compact support of the generic fiber with the value in our original sheaf. And the conjecture is that we hope to prove that this map is always an isomorphism. We know that when the stack of shtukas is proper, this is a theorem of Grothendieck. And what we want to prove is that in general, even when the shtukas is not proper, we still have this isomorphism. So here I only state it for one like. We have a version of this conjecture for general I and W. A little more complicated to state, so I didn't write it down. And recently there is a PhD student, Andrew Salmon, who proved this conjecture for the case of parahodric level. So his paper is already on arXiv. So that's about on the level. So in the rest of the talk, I will talk about the proof of the theorem. So are there questions until now? So I continue. So to prove the smoothness, we don't use the compactification of stack of shtukas. Instead, we use a lot of the partial Frobenius morphism, which is a very important property on stack of shtukas and their cohomology. So I began by the partial Frobenius morphism on stack of shtukas. So we consider a stack of shtukas with the I is this set, and W is like this. So W is a representation of I copy of G height. So each W1, W2 is a representation of G height. And so the stack of shtukas, we say that it classifies the likes and a chain of modification of G bundles. The last one is the inverse image of Frobenius of the first one. We can send this stack of shtukas to a similar stack of shtukas who also have K likes, but the order of modification is a bit different. So for this second stack of shtukas, for the first modification, it is bounded by W2. So for the first shtukas, the first modification is bounded by W1. For the second shtukas, the first modification is bounded by W2, etc. And the map is that we keep this part of the chain. We keep we keep G1 until the dou G0 part. We put it parallelly here, and then we cut the G0 to G1. We add Frobenius on G0 to G1 modification, so it becomes tau G0 to tau G1 modification, and tau G0 we can add it here. So we use Frobenius applied to this and put it at the end. We can do this because this chain is finished by tau G0 by the Frobenius. And what happens on the likes is that here you have modification on first like, second like, and here the KZM like. And here This modification is on second leg x2. This modification is on third leg. This phi k is on k's leg, and the last modification is on Frobenius of the first leg. So the modification here sent to this one. So on the bus line, what happens is that you just have a Frobenius for the first factor and identity for the other factors. So I write down the partial Frobenius for this one, and then you can do the same things for this one, which means you can keep this chain and put Frobenius of G1 to G0 from G1 to, then you add Frobenius of G1 to G2. It becomes tau G1 to tau G2. You add it here. Like this, you can do a Frobenius for the second one. For 2, you can iterate this until k times. So if you compose this until k times, at the end, you will arrive at something like tau G0 to tau G1 to tau G2 until the last one is tau of tau G0, which means the composition of this is the Frobenius of this one, is the total Frobenius of this one. So you're back to the same stack of shtukas. So in the middle, you pass from some other stack of shtukas, but at the end, you refine your original stack of shtukas. That's why these morphisms are called partial Frobenius morphisms, because their composition is the total Frobenius morphism. And this partial Frobenius morphism on stack induce partial Frobenius morphism on the cohomology. Here, something I didn't say is that these two stacks of shtukas, very similar but different, they have the same cohomology, the same relative cohomology. So on the level of cohomology, when you do the partial Frobenius, you always stay on the same cohomology. So you get the partial Frobenius morphism on the relative cohomology shifts. Here is the relative cohomology shifts is lives on x power n power I, so they are on this. Oh, I forgot to write minus n. So they are on this. So here you have the H. You take the Frobenius I inverse image of H. You arrive here, and here you have a H2, also a H, and we have an isomorphism. We can construct a canonical isomorphism between these two. So this is Frobenius on x times I, x minus n times I. So you have Frobenius for first leg, for second leg, for each leg, and the composition of this is the total Frobenius morphism on the cohomology. So this calls the partial Frobenius morphism on the cohomology. So now let's say what we have on the cohomology. We can also consider the generic geometric fiber of the cohomology. So we note eta I, the generic point of I copy of the curve, and eta I bar, a geometric point over eta I. And usually what we call cohomology group of stack of shtukas is the geometric generic fiber of the cohomology sheaf. And so the cohomology group is a QL vector space. It may have an infinite dimension. As the space of automorphic forms, it may have infinite dimension. The cohomology group is equipped with the following action. So first we have an action of Haeckel algebra by the Haeckel correspondence. It's like the Haeckel correspondence for the Shimura varieties. And then we have an action of pi 1 of the I copy of the curve, because it's a geometric generic fiber. And what is special is that we have partial Frobenius morphism here. So for the analog of partial Frobenius morphism for cohomology of Shimura varieties, there are Ziyu Wu who work on some of this. So if you are interested, you can look at his work. So we have this. What we will do next is that Drinfeld has a lemma which allowed us use this and this to relate these two actions to the Galois group of the function field. We are interested in Galois group of the function field, but which is different of this. So here are the relations. We note eta the generic point of X and eta bar geometric point of generic point, and we have the Galois group of the function field of the curve. We have a map from the pi 1 of the generic point of Xi to the pi 1 to I copy of pi 1 of the generic point of X. So in this line, in the first line, we are it's pi 1 for the I copy of the curve. So you have only one Z height. For the second line, it's I copy of the pi 1 of each curve. So in the second line, you have I copy of everything. So you have I copy of that. So you'll see that the pi 1 of the Xi is very different from I copy of the Galois group. Drinfeld's lemma says that for the original form is that for a finite dimensional QL vector space, and if it is equipped with an action of V group of eta I, so V group is a V group in the Galois in the pi 1 correspond to Z. If it has an action of V group of eta I and an action of partial Frobenius morphism, and then it is equipped with an action of I copy of the V group of eta. So V group of eta is a V group in pi 1 of eta. And a slightly more general version for Drinfeld's lemma applies not only to finite dimensional QL vector space, but to finite type module over a finite generated commutative QL algebra. For example, a finite type module over a local Haeckel algebra is in this case. So for finite type module over a local Haeckel algebra, if you have an action of V group of eta I and action of partial Frobenius morphism, then you get action of I copy of the V group. So apply to the Drinfeld's lemma to the generic fiber of cohomology, we get an action of I copy of the V group on the generic fiber of cohomology of shtukas. There are two ways to get this. So the first way is that we can use the constant term morphism for cohomology of shtukas and prove that the generic fiber of the cohomology is a module of finite type over a local Haeckel algebra. Then we apply directly Drinfeld's lemma to the generic fiber of cohomology. But the constant morphisms are only written for split reductive groups. For no split reductive groups, there should still be the constant morphism, but they are not yet written down. And another way to get the proposition is that we don't need this result. Where is this result? We can use some weaker result. So we use the Eichler-Schmurer relations for the partial Frobenius morphism. We can write the generic fiber of the cohomology as an inductive limit of finite type module over some local Haeckel algebra, and we apply Drinfeld's lemma to each of these finite type module over some local Haeckel algebra. It's enough to show that. So for apply Drinfeld's lemma to each of these finite type module over local Haeckel algebra, we get action of I copy of V group on each of these. It's enough to get the proposition. The advantage of this way is that it's easy to write down for all reductive groups. So that's this is the proposition we will use in the to prove the theorem. And here is another proposition that we need. So the restriction of the relative cohomology sheaf on this integral scheme. So we take eta bar times eta bar over FQ bar. So this one is an integral scheme, and we restrict the relative cohomology sheaf on this one. It is a constant sheaf. So what does this proposition says? In fact, if the cohomology was of the form the product of some sheaves, then the proposition 1 and proposition 2 are automatically true. But unfortunately, the cohomology sheaf may not of this form. So here these two propositions say that even they may not of this form, but it still has some property that the product of the sheaves has. For example, it is constant over this kind of integral scheme. And we use this to prove the theorem. So before I prove it, I state the theorem again. So in the unsmooth, there are two definitions. One is that it's inductive limit of smooth QL sheaves. Another definition is that for any geometric point, X bar, Y bar, and any specialization maps, the induced morphism of the specialization map is an isomorphism. So these two definitions are equivalent for smooth sheaves, but in fact they are also true for limit of, and they are true for constructible sheaves, and they are also true for inductive limit of constructible sheaves. And in the proof, what we really prove is this equivalent definition. We prove that for all specialization map, the induced map is an isomorphism. And before go to the proof, immediate corollary is that the action, the I copy of V group, it factorized through the V group of X minus N. So to give the proof, to give idea of the proof, I talk only in the case when I is a singleton. The general case is the same, and we consider without level to simplify. So now we have a cohomology sheaf over one copy of the curve. And what we want to prove is that for any geometric point of the curve and any specialization map from generic point to a geometric generated point to this V bar, the induced map is an isomorphism. So what we do is that we will contract a map from the other sense, from the from cohomology district to eta bar to cohomology district to V bar, and show that it is the inverse of this map. And to contract the inverse map, we use creation and annihilation operator of Weil and the propositions we proved before. So here is a way to construct an inverse map. We began from the cohomology when one leg restricts to the generic point. The creation operator of Weil allow us to create two more legs. And the two more legs, we can ask them to be on the place V bar. So we create two legs. They are the same legs too. They are both on V bar. And for the two legs, we can give their representation correspond to dual of W. So it's a dual. For the second leg, we give its representation the dual of W. For the third leg, the representation is the same as W. So now we have cohomology of stack of shtukas with 3 legs on eta bar, V bar, and V bar. We can use the proposition we proved before to contract a canonical morphism which move the second leg from V bar to eta bar. So this map, we don't touch first leg and second leg and third leg. We only move the second leg from V bar to eta bar. So how to think about this map? If the cohomology of shtukas with 3 legs can write as product of F1, product F2, product F3, then you have canonically this map. So if the cohomology with 3 legs is on the form of product of shifts, this is evident. And here what we do is that we use the proposition. We proved before that they have the property very similar to the product of shifts, and we arrive to construct this map. So now we arrive at a cohomology of shtukas with 3 legs. First leg on eta bar, second leg also on eta bar, and third leg on V bar. Now we can apply an annihilation operator to cancel first and second leg because they are both on eta bar. we can do this. So the first and second leg go to the constant Rive, and we only have the third leg, which is on V bar. So if we compose all this, we get a map from this. Now we want to show that this map is the inverse of the specialization map. Inverse of this map. And to do this, we need something more, which called the Zorro lemma, which comes from the Zorro lemma for the vector space. So if W is a vector space, and we consider the following composition, we send the first one to the first one as identity, and we send QL to the dual of W tensor W by the canonical map. And then we apply evaluation for the first one and second one. We get arrive to QL, and for the third one, it's an identity. So it looks like a Zorro, and the composition of this is identity. And by the so there are something I didn't say is that the cohomology of shtukas is functorial to W. So when you have some morphism for W, you get the same for cohomology. So for cohomology of shtukas, we get the same things from. That's why we choose for the second and third leg the cohomology. The W we choose dual of W and W. So after creation, two legs on W dual and W, and then annulate the first and second legs. The composition is also identity. So now we prove the map we construct is the inverse of the specialization map. So here is the specialization map for shtukas in one leg from V bar to eta bar. And here vertically is the map that we constructed. And on the left hand side, it's also creation two legs so on left hand side, all three legs are on V, and we create two legs on V, and we cancel two legs on V. On the right hand side, we create two legs on V, and we cancel two legs on eta bar. The composition of the so for the right vertical morphism is what we constructed, and for the left morphism, it's the Zorro lemma. So to apply Zorro lemma, all the three legs should be on the same place. So the three legs should be this one is on the diagonal. I forgot to say that delta means diagonal of X in X3. So in the left-hand side, where all the legs are on V, so by Zorro lemma, we know the composition is identity. So now we know that specialization composed with alpha is identity. And to say the alpha composed with the specialization is also identity, we do the same things, but here the right hand side we use legs. All the three legs are on eta bar now. And since all the three legs are on eta bar, we can use the Zorro lemma. So the right hand side are identity. So like this, we prove that this composition is also identity. So we show that this map is the inverse of the specialization map. Like this, we prove the theory. Yes, I think I finished.
Okay, thank you. This was great. Are there questions? Well, I had one technical question. In the definition of the inverse map, you use this split 2 upper star, the specialization map, and this just a second variable. And you said this comes from proposition 2, but I was slightly confused about this because you're somehow not. Proposition 2 only says something about the fiber product of the geometric generic points, but
yeah,
you're still at a special point in one of the coordinates.
Yes, because
how can you use? So there's some kind of secret variant of proposition 2 that's used, or?
Yes. In fact, there is a proposition 3 I didn't write down. So there is a more general version of proposition 2 is that you can replace any of this eta bar by Weil bar. So you can have eta bar for times eta bar times eta bar, eta bar times Weil bar times Weil bar, eta bar times Weil bar times eta bar. And in fact, in the proof, you need to use all this version, all this combination possible.
Okay, great. Thanks.
So here, I only write for the second leg, but in the proof here, you need to use the same construction to contract these two maps.
Right. And I had one further question about the formulation of this theorem with nearby cycles in the higher dimensional case. So do you use the theory of high dimensional nearby cycles there? This is something I've never really properly understood. So.
Yes, that's a problem.
But I mean, I guess one version that like one version of the conjecture one could state is that whenever you have any kind of valuation ring mapping to x to the I, say with algebraically closed fraction field, then you could somehow pull back to this valuation ring and then takes nearby cycles just in this one direction given by this valuation ring. Is that somehow more or less equivalent to what you're conjecturing, or?
What I think to use is the nearby cycle of high dimension of orthogonal. Orthogonal.
Maybe one question there. I mean, they usually first have to do a blow up before the nearby cycles become nice or something like this. I forget how this works really. Is part of the conjecture that the blow up shouldn't be necessary, or should the blow up be necessary?
I do not know. Perhaps the blow up are hidden on the formulation.
Okay.
But it seems that although have a definition of nearby cycle for a general base, we can define a nearby cycle like this, and I think that's what I want to put for the general version of the conjecture.
Okay.
But perhaps for other version of nearby cycle, we can have other conjectures, and they are also true.
Right. How does you said that Andrew Solomon proved this in the case of parahoric level?
In this case, we can calculate everything And in this case, the nearby cycle for a general base is the same as the iteration of nearby cycle for each dimension.
Oh, I see. That's cool. Okay. And then to prove that the map is an isomorphism, do you use a strategy similar to the one you presented, or?
Yes, the proof is very similar to the proof of the theorem. You use Zorro lemma.
Thanks. Any other questions? That doesn't seem to be the case. So yeah, let's thank Cong again.